while ago, a friend of mine asked me to describe the basic concepts of calculus in a way that is comprehensible to a person who is not a math student, not a lot of background in mathematics, but just curious about what these things mean. What are its basic concepts? How do they work together? And how would you use it to solve certain kinds of problems without any technical background at all, just a purely conceptual understanding of calculus. So, as it turns out, those concepts are not particularly hard to understand. They are very intuitive, very physical, very conceptual, or geometric. So it's a good thing it should be possible to do that and to convey that in a way that more or less anyone can understand. So this is an attempt to do that. And so to begin the discussion, what we do is we imagine a car driving on a track. So it's a completely straight track, no curves or anything in the track. We have a starting line, which we will consider to be zero distance. And we'll have a stopwatch, and the stopwatch starts at 0, and then when we push the button on the stopwatch, the car starts moving. It can move forward along the track, it can move backward along the track, however it wants to. There's no turning, it's just back and forth. And so we're going to record two things about the car. We're going to, at all points in time, we're going to record where it is on the track, and we'll use metric units of meters, and we will also record how fast it's going, and we'll use meters per second as the measure of speed. So, so just imagine that we've got a straight track, and the pen has dried up. All right, that's good. Left it open. All right. So we've got a straight track. We've got our starting point. And I'm looking down on the track here. So we've got a car on the track. The starting line is where what we'll consider to be distance equal to 0. And we will push the button on the stopwatch and the car will move back and forth along the track. However it wants to. We can go backwards behind the starting line, that would be a negative distance. Moving forwards, we consider to be positive velocity. Moving backwards, we consider to be negative velocity. And everything that you need to know about calculus can be understood in the context of this very simple scenario of the moving car on a straight track. Okay, so there are two fundamental concepts in calculus. The first one is called the derivative. And the second one is called the integral. So we need to, these things were actually invented historically for the purpose of studying speed and motion, very much like we're going to do here. So we'll talk about what these terms mean and their geometric implications, and more importantly, even than those concepts, is the way that they relate to each other. There is something called the fundamental theorem of calculus. And that describes the way that these two basic operations of calculus relate to each other and enable us to solve some very complicated problems in relatively straightforward terms. Okay, so now let's begin with the derivative. And To talk about the derivative, the problem that we're going to consider is first, how do we determine, based on the position of the car over time, how fast it was going? So let's draw a graph of the position of the car over time. So on the x-axis will be time in seconds, and on the y-axis will be distance in meters. So we already said that at time 0 the car is at the starting point, so we'll start our distance at 0 meters. And then let's just say it does something simple like it starts driving forward, it accelerates to a constant speed, stays there for a while, and then it comes to a stop, and then it starts going backwards, and maybe it passes back across the starting line, so now we're at negative distance, then it stops again, then it comes back forward to the starting point and stops completely. Okay, so this is a basic graph of distance over time. So as I mentioned, what we want to do is use this graph to study what is the speed of the car over time. We don't have that information here directly, but we can figure it out using geometry and calculus. So derivative is the tool that's used for this type of thing. So now, one thing to notice about a curve like this, the way that it's drawn, it's nice and smooth. There's no jerkiness or anything. The car didn't smash into a wall or anything of that nature. It's smoothly moving. If you were to zoom in on a small piece of this graph and blow it up, then over this relatively short period of time, then it looks much more like a straight line because you don't have any of this stuff out here. So this small piece of the graph ends up looking something like that, just a straight line. If we were to then zoom in further on a tiny piece of that graph and blow it up, then it looks very much like a straight line, almost perfectly straight. And of course you can continue that process ad infinitum as long as you want, continually zooming in, and the more you zoom in, the more like a straight line it's going to be. So that is, in a nutshell, how we determine the speed given the position. So let's look at one of these extremely close-up views of our position curve. So we have 2 points in time. We'll call them T1 and T2. These 2 points in time might be milliseconds apart. They're very, very close together. And then at the point T1, we're at a distance D1 from the start of the track, and at T2, we're at a distance D2 from the start of the track. So because it's a very straight line, well, the velocity, or the velocity of something moving in a straight line is very simple, right? That it's a constant velocity. It doesn't change. You have something just, the car is cruising at a constant speed down the road. So the graph of that looks like a straight line. And so by choosing 2 points in time like this that are very close together, we get a very good approximation of what the speed of the car was at that time. Now, it's not exact because there is, even if we can't see it, there may be a very, very slight bend in that curve. But the point is that we can take these 2 points in time as close as we want them to be. And the closer we bring them together, the more like a straight line that the graph actually becomes between those 2 points. And the better an approximation that that nearly straight line is of the actual instantaneous velocity of the vehicle at that point in time. So, so to determine what that actual velocity would be, well, speed velocity is the difference in the distance divided by the difference in time. It's how far you went and how long it took you to get there. So that is simply d2 minus d1 divided by d2 minus t1. So we can choose these 2 points in time arbitrarily. The distance is determined by our graph, and the closer we make those 2 points in time together, the better an approximation of the velocity that we get. And we can furthermore do this process anywhere along this curve at any 2 points in time that we want. Well, this is not quite the exact velocity. It will never be the exact velocity because you'll always be working with 2 different points in time, and the car will have, unless it's stationary, it will have moved a little bit in that point in time, and there will be some perhaps infinitesimal variation in the velocity over that period of time that this approximation is never exactly correct. But what we do is we imagine, though, that as these 2 points in time are brought closer and closer together, that the ratio of change in distance divided by change in time starts getting closer and closer and closer to the true velocity, instantaneous velocity, and we presume that there is an instantaneous velocity, that there is a real true number that where your needle is pointing on the speedometer at that point in time is the true velocity. So, so we imagine a process by which we can bring these 2 points towards each other forever, even to the extent that they actually are the same. We can't really make them the same, but as they come closer and closer together, the ratio will be getting closer and closer to some number, which is the true velocity, and that true velocity that's determined by this process is what we call the derivative. That is the derivative process, forming quotients of this kind, bringing the 2 points closer and closer together, and seeing what number they are getting forever closer to. That is the derivative. And another thing that's very important to take notice of when you're doing this type of process is the units. That we are forming quotients. The numerator of the quotient is distance, which is in meters. And the time part of it is in seconds. We're dividing meters by seconds. Those are units of velocity. So you take a curve which is the y-axis is distance, the x-axis is time. You're computing velocities with the derivative by forming these quotients. In general, there's nothing special about distance and time. These can be any 2 quantities you ever care to work with or care about. You can form a derivative, which is this type of infinitesimal quotient. And that's it. That's what the derivative is. Okay, so now we're going to basically turn this on its head, and we're going to start at the opposite end. So what we're going to do now is, instead of being given the distance and determining the velocity from the distance over time, we're going to go the opposite direction. We're going to take the velocity as it changes over time, and we're going to determine the distance given the velocity. So now we draw a different graph based on the motion of our car on the track. So we still have time on the x-axis in seconds, this way, and And we have velocity on the y-axis. Velocity, in this case, we're going to measure in meters per second. And that's the y-axis. So the car started from a standstill at the starting point, so we begin here. And then over time, the car will gradually rise to a certain constant velocity, and let's say that it continues at that constant velocity for a period of time. And then it starts decelerating and actually crosses zero and starts going backwards. And then maybe cruises at a constant velocity for a while and then comes back to the start and stops. Okay, so I didn't draw it very well, but let's say that these are the points at which the car was basically cruising at a constant speed and then just transitioning between those. Forwards here and backwards here. So, okay, so now what we want to do is look at this curve and determine how far did the car go during this period of time, only knowing what its velocity was. Okay, so the way that we approach that is, in general, for a curve, we can't really do this, but again, we sort of imagine this zooming up process, right? We take a part of the curve and we blow it up really big. Well, again, as we keep zooming into the curve, it starts to look more and more like a straight line. So take another piece of this, blow it up again, continue the process, again, even more like a straight line than it was before. You zoom in really, really, really close, and it looks like a perfectly straight line. So now let's look at what units we're dealing with here. So this is velocity. And we've got 2 points in time, which again we'll label T1 and T2. And then we have 2 velocities, V1 and V2. Okay, so now this basically forms a trapezoid. And so in order to determine the distance that the car traveled between these 2 points, it's basically, it's the area of this trapezoid, right? So it's basically, if it were a constant velocity, a strictly straight line, then it's the area of the rectangle. So we can approximate, let's just say that we take the midpoint and that was, we use that as our velocity over, our fixed velocity over the interval. So we can approximate the distance traveled between these 2 points in time as being the area of this rectangle, so we'll just call this one V. So it's simply we're multiplying now. Velocity times T2 minus T1. The amount of time that it took and the velocity that was traveled at during that period of time. Now, that only gives us the distance traveled over a very small infinitesimal point in time. So what we need to do is form this type of rectangle and add them all up across the whole thing. So you imagine dividing time up into a whole bunch of tiny little pieces all along the way here. And I won't draw them all, but this is it, and draw the little rectangles in there, and so on. So the area of, basically each one of these rectangles represents the distance traveled over that little short period of time. And then to get the total distance traveled, well, we just add up the distance traveled along each of the tiny little increments of time. And so what we end up with is something that looks like this. We'll do our first velocity times the first increment of time, and then we're going to add to it our second velocity times the second interval of time, etc., etc. And we're going to do that all across our whole period of time that we care about. Now, by making each point in time, or each time interval, smaller and smaller and smaller, then we get more and more little rectangles over which we are calculating our distance. And as we make those intervals smaller and smaller, the approximation becomes more and more accurate over time. It's kind of like the progressive zoom in. The more you zoom in on a little piece of the curve, the more flat it becomes. So, so just continue that process as we make the rectangles smaller and smaller, and you can imagine that as the rectangles are getting smaller, this whole total sum distance from end to end is first of all becoming more and more accurate with respect to the actual distance traveled as it went along its whole course of motion. But not only that, that as those intervals become smaller and smaller, the value is approaching some specific single number, which is the actual distance. Okay, so if we were to imagine making these infinitely small, which we can't actually do, of course, but we can look at the trend that happens as we make the intervals smaller and smaller and just see what number it's actually approaching. So that process of forming these little rectangles and adding them up, that process is called integration. And that is how we get from velocity to position in this particular case. Also, let's take a look at the dimensions that we're dealing with. So each one of these little things that we're adding up, these products, which correspond to the areas of rectangles underneath this curve, we're multiplying velocity, which is meters per second, and we're multiplying it by seconds. So, so the resulting unit of that operation is meters, which is exactly what we would expect. We're trying to determine distance from velocity. Distance is in meters. We are multiplying meters per second times seconds. So, so the result ends up being meters as we expect. And that's it. That, in a nutshell, is what integration is. It's basically chopping up small pieces of time, multiplying and adding. And that gives us position from velocity. That's it. The two basic concepts of calculus, derivative and integral. Again, to recap, physically, the derivative takes you from position to velocity. The integral takes you from velocity to position. These are by no means the only applications of these types of operations, but they're very familiar and physically intuitive and easy to understand. So now, what we want to look at is the relationship of these operations to each other, which is the fundamental theorem of calculus. So, the way that we understand that is to look at the position and the velocity at the same time. So let's draw these two curves together on the same page. So we'll just bring both of our graphs back. So our position, we kind of increase to a constant speed, went that way for a while, turn around, again go at a constant speed in the opposite direction and come back. And then our velocity, we rise to a constant velocity, kind of go that way for a while, we slow down, we turn around, go at a constant velocity again for a while and come back. So position, velocity. Now, we already said that differentiation is the process of, for example, going from position to velocity. So getting from this graph to this graph, that is differentiation. On the other hand, going from velocity to position, basically going the opposite direction, that is integration. Now, naturally, what becomes interesting about this picture is to think about, okay, what if I start with a position curve and then I first differentiate it to get velocity. But then once I've gotten the velocity, I turn around and integrate it again to get position. So sort of making this round trip through this process. Take a position curve, differentiate it, and then immediately integrate it. What is the result of doing that? Well, if it's the same car that we're talking about, simply going from its position to its velocity, and then going from there from its velocity to its position, well, that should naturally just lead you to the exact same thing. If you take this curve, differentiate it, and then integrate it, you should have the exact same thing. It's a single car, it can't suddenly change or do something different. Likewise, we can go the opposite way. We can start with velocity, integrate it to get position, and then differentiate it to get velocity again. Repeat that process, same thing. If you start from a certain velocity curve and you integrate and then differentiate, you should wind up with exactly the same thing again. It's the same car, nothing about it changed. So either way you go should simply return you back to the starting point that you had. So let's just try to draw a picture of that. So whether we're going this way around or whether we're going this way around, no matter what, your starting point should be the same thing as your ending point. In other words, differentiating and then integrating something brings you back to the same. Likewise, integrating and differentiating something, again, brings you back to the same. It's very clear from this picture and physically obvious that this is what happens. And that is the fundamental theorem of calculus, which expresses the relationship between these two basic operations. And that's it. That's the whole thing.